Types of hybridization with shapes. In this, there are two types of hybridization. One is of sp3d2. This is sp3d2 dehybridization, not d2. It is sp3 dehybridization, in which one s atomic orbital mixed with three p orbitals, that is px, py, and pz, and one d atomic orbital, that is dz square, and forming the trigonal bipyramidal shape, in which the bond angles are 120 and 90. For example, in case of PCl5, phosphorus is the central atom, which is attached to 5 chlorine atoms. 3 are in the equatorial plane and forming a triangle with bond angle of 120, and the fourth chlorine is above the plane and fifth below the plane. These are on the axial axis to avoid the repulsions, minimum repulsions in this case when they are far from each other. That's why they lie on the axial axis. These two chlorines, one above and one below the plane, for the minimum repulsions. And the shape of the molecule is trigonal bipyramidal. Its hybridization is sp3 dehybridization. And in case of sp3d2 hybridization, one is the s atomic orbital, 3 p atomic orbital, and 2 d atomic orbitals are mixed together to form 6 new hybrid orbitals and forming the shape of octahedral. For example, as in case of SF6, 4 fluorine atoms lie in the square planar and 5 on the above the plane and 6 below the plane, forming the octahedral shape, and the bond angle are 90, and the shape of the molecule is octahedral with hybridization sp3d2. Next type of hybridization is sp3d3 hybridization, in which one s atomic orbital mixed with 3 p orbitals, that is px plus py plus pz, and 3 d orbitals, and they form 7 new hybrid orbitals. For example, in case of IF7, I is the central atom and 5 fluorine atoms lie in the one plane, 6 above the plane and 7 below the plane, and the geometry of the molecule is pentagonal bipyramidal with bond angle of 90 and 72 degrees. Predicting hybridization of central atom. For predicting hybridization of central atom, there is one formula in which X is the central atom, which is equal to 1 by 2 VE, where V is the valence number of valence electrons of the central atom. Ma is the number of monovalent atoms, means monovalent atom means which carries a -1 or +1 charge, and C is the charge on the cation, A is the charge on the anion. For example, in case of CO2, carbon dioxide, C is the central atom. Here we will calculate the hybridization of carbon. 1 by 2 into Number of valence electrons of carbon. Atomic number of carbon is 6. It means it has 4 valence electrons. 4 electrons in the outermost shell. Plus monovalent, number of monovalent atoms according to the formula. But here oxygen is not a monovalent atom. It is a divalent atom because it has -2 charge on it. And C is the charge on the cation. There is no charge on the carbon atom. In case of monovalent, there is no monovalent atom present in carbon dioxide. That's why it is 0. And no charge on the carbon. It is also 0. And no charge on the oxygen O2. It is also 0. By calculating it, we get 2. It means carbon has 2 hybrid orbitals. That is sp. And the hybridization of carbon is sp in case of carbon dioxide. Now let us take another example for more illustration. For example of BF3, boron trifluoride, in case of boron trifluoride BF3, boron is the central atom. B, we will calculate the hybridization of boron. 1/2 number of valence atoms, electrons in the boron, that is 3. Its atomic number is 5. Boron has atomic number 5. It means it has configuration of 2 and 3. And 3 are the valence electrons, means electrons in the outermost shell. Plus 3 monovalent atoms. Fluorine is monovalent because it carries -1 charge. That's why it is monovalent. And here it is 3 number of fluorine atoms which are attached to the boron. And here we write 3 minus, there is no charge on the boron and no charge on the anion fluorine. By calculating it, we get boron is equal to 3. It means it has 3 hybrid orbitals. That is, its hybridization is sp2. It means boron has sp2 hybridization in case of BF3 molecule, and it has trigonal planar shape with Born angle of 120 degrees. Next is coordinate bond or dative bond. Coordinate bond is that in which lone pair of electrons are donated by one of the atom to the electron deficient molecule, and this lone pair is shared by both the atoms so as to complete their octets, and the bond formed is called coordinate bond or dative bond. For example, as in case of ammonium ion, NH3 is the ammonia which has one lone pair of electron. As you can see in the orbital picture, it is a lone pair of electron on nitrogen, and this is the 1s empty atomic orbital of H positive. This lone pair of nitrogen is donated to this H positive empty 1s orbital, and it forms a coordinate bond. It is shown by this black arrow. This is the coordinate bond, and this lone pair is shared by both the atoms nitrogen as well as hydrogen. And nitrogen here carries positive charge because nitrogen forms only 3 bonds, but in this case it forms 4 bonds. That's why it carries positive charge. Another example, in case of ammonia and BF3, here nitrogen has 8 electrons in their octet, but in case of boron it has only 6 electrons. It means it is electron deficient. And nitrogen has one lone pair, which is pair, and this pair, lone pair, it gives to the boron atom and forming a coordinate bond like this, so as to complete the octet of both the atoms, nitrogen as well as boron. They share this lone pair with each other. Next is resonance. Resonance, which represents the delocalization of electrons within the molecule. For example, as in case of NO2 molecule. In case of NO2 molecule, nitrogen has double bond with one oxygen and single bond with other oxygen, and it carries one minus charge, and this charge is transferred to the single bond, means these electrons are transferred to the single bond, and this double bond is transferred to the other oxygen, and it forms O negative, and this is double bond O. This is structure number 1, and this is structure number 2. These two structures are called as resonating structures or contributing structures. These two structures are canonical forms, contributing structures or resonating structures. These two structures alone cannot explain the properties of the NO2 molecule. It means there is some another structure which explain all the properties, which is represented by these 3 arrows, these 3 lines, and here it is N, O and O, and this is the delocalization of negative charge, and this structure is called as resonance hybrid. This resonance hybrid explains all the properties of NO2 molecule, and this structure is the resonance hybrid. First and second structures are the resonating structures or contributing structures. Next example is ozone, in which 3 oxygen atoms are attached with each other, like in this structure, one oxygen with double bond O and other with single bond O, and it carries minus charge, and it here carries plus charge because oxygen forms only 2 bonds, but in case of ozone it forms 3 bonds. That's why it carries plus charge, and these electrons are transferred to the single bond, and this double bond transferred to the other oxygen, and it forms another resonating structure like this, way, and the resonance hybrid of ozone is like this. Here is the delocalization of electrons over the entire molecule, means all the three oxygen atoms. And this is the resonance hybrid of the ozone. And this phenomenon is called the resonance. Resonance energy. It is the difference in energy of resonance hybrid and most stable canonical form or resonating structure. Most stable canonical form. And this difference between the energies of resonance hybrid and most stable canonical form is called resonance energy. This is called the resonance energy. Resonance hybrid has the lowest energy, and the energy difference between the resonance hybrid and the most stable canonical form is called the resonance energy. Next is the characteristics of resonance. Resonance hybrid has the real existence but not the contributing structures. It means contributing structures are just imaginary structures. They have no real existence. The second point, as a result of resonance, bond length in a molecule becomes equal. As we have already studied in the last slide, that ozone has the equal bond length because of delocalization of these electrons over the entire molecule. These pi electrons over the entire molecule. That's why its bond lengths are become equal. Next is the resonance hybrid has the lower energy. Lower energy means greater stability. Next point, greater is the resonance energy, means this energy. If this energy is greater, then stability of the molecule is also greater. Greater the resonance energy means greater is the stability of the molecule. And the next point is greater is the number of canonical forms, greater is the stability of the molecule. If the number of the canonical forms are more, means the molecule is more stable.